All
Good
right,
morning.
thank you. All right, that's fine. Okay. Last week we started this new topics. From session 1 to session 6, we have been covering quite troubleshooting fundamentals and some of the basics as well in terms of network troubleshooting. Then from the last week, which is the session 7 to 7 onwards, we'll be starting a bit of more advanced topics. So in terms of the coverage on the last week, we discussed on unicast, broadcast, and multicast transmission, and we had a comparison between three modes of transmission. So basically, the most famous one is unicast, and you have been understanding on the broadcast as well in terms of your the first semester courses will be mostly covered on unicast and broadcast transmissions. But we'll be discussing details here on the multicast transmission, especially targeting the multicast troubleshooting and multicast security implementation. So then thereafter, I was covering few topics on the IP multicast fundamentals. So this was the overall coverage in terms of the different traffic types. Unicast was broadcast, was multicast discussed, and we discussed on UAM traffic. Then I covered on IP multicast fundamentals with the requirement of IP multicast and the multicast history and fundamentals and the use cases and the applications. And there are certain assumptions with the multicast implementation, which we call multicast considerations, and some of the components discussed. Then the addressing model, which is having a different IP addressing scheme for especially dedicated for the multicast. Then we discussed a bit on multicast service model. A couple of more topics to be covered in terms of IP multicast fundamentals, layer 2 multicast and layer 3 multicast, that we can cover up on the first session. Then we can start on the IP multicast troubleshooting fundamentals and the details there. Finally, I'll be discussing IP multicast troubleshooting best practices. On the next week, for the first session, I'll be giving you IP multicast security implementation best practices and the troubleshooting in there as well. So this will be the coverage for 2 sessions on today and the next week. So then in terms of the what we have already covered, marked by green, and I will be starting on the layer 2 multicast, but I will do a small recap on you because now we are meeting after a couple of weeks, I guess. Okay, we had a detailed discussion on this unicast versus multicast, and if you are having multiple receivers, you need to send 3 different sessions or initiate 3 different sessions from the server side or the rather sender side up to the receivers connected through unicast. But in terms of if you are sending, that's fine if you are sending 3 different or different messages to the receivers. But if you are sending something like same message to all the participants or all the receivers, then there is no necessity to send multiple sessions through message through multiple sessions. It's a waste of bandwidth, waste of computing resources on the servers and server side. So if you are sending same message to everybody, then the best way to implement that by using multicast. So if you are sending a multicast stream from a server to receivers or sender to receivers, then you just send one copy of it to the first stop router, and then it's replicating to other routers just by sending one copy to each path and until up to the receiver gets it. this is the idea behind the multicast, to save the bandwidth as well as reduce the computing resources, which is quite helpful in terms of the scalability of your network, and the limiting the unnecessary bandwidth utilization or the unnecessary overloading. Uh, so that's the idea behind between unicast and multicast. Okay. Then this is another representation of same idea, but additionally, in terms of multicast, you can see that left side is based on the unicast streams. The right side is based on multicast streams to come for the comparison. The sender is sending there are three receivers or three receivers, and there is a one who doesn't the sender doesn't want to send the message, or receiver doesn't want to get involved in receiving messages from the sender. Uh, so the receivers getting three different messages based by using unicast. If sender hasn't addressed anything to the receiver's IP address or the MAC address, then it doesn't get involved in the communication. That's you can see on the right side of the branches, and then on the right side of the multicast tree, you can see that sender is sending just one copy to the first hop router, then it's duplicating or the replicating to other receivers. If you can see on the right side of the same diagram, still who is not intended to receive the stream or the message, not getting the message similar to the unicast. So that's the idea. But for the broadcast, you can say if you send a broadcast, most probably, if you are in a broadcast domain, the unintended receivers also getting the same message, same message. So there is no restriction, but by using multicast, you can restrict this. Only the receivers getting, but non-receivers or non-intended to receive the message will not get the message. Okay. Then we had another diagram to compare between broadcast versus multicast. So in a broadcast, previously the comparison is on unicast versus multicast. Now it's broadcast versus multicast. So if if you send a broadcast from a from one of the hosts, so all the everybody in the network will be, or within the broadcast domain, will be getting the message, even it's not made a request to receive the message. That's the difference between multicast and broadcast. But multicast, you are only getting if you signal the requirement of receiving that particular the message stream or the that's the difference between broadcast and multicast. Broadcast, even if you are not intended to listen the message, you are still getting it. But for the multicast, you need to signal the request to receive it. So that's the difference between multicast and broadcast. So then we discussed on the traffic named as bump traffic, which is called broadcast, unicast, which means unknown unicast, and the multicast. All these three types of traffic usually replicated in your broadcast domain, which means if there is a VLAN or the local area network, you are flooded with this traffic by default. So the idea is to manage these three types of traffic in a formal way by implementations, rather than in a modern day networks. Usually there is something called VXLAN, it's the same terminology as similar to the VLAN, virtual LAN, which is the segment of broadcast domain, which you are receiving all the broadcast, and everybody getting unknown unicast and the multicast. So basically, when you are implementing VXLAN requirement, usually comes through the limited number of VLANs available for the traditional technologies for the data centers. Nowadays, for the security reasons, the isolations of failure domain is necessary. So more number of VLANs required. The maximum number of VLANs we can get uh, somewhere around 1,000 VLANs, or if we are using another mode, we can get maximum of 4,000 plus VLANs. But if in modern data centers, you require more than that, and a new concept called VXLAN implemented to cater the failure domain requirements. In this VXLAN implementation really require you to address on the broadcast, unknown unicast, and multiclass. Otherwise, entire network or the entire data center will be flooded and it's affected. So there are several ways to handle this, which we will be not discussing in details, just for your understanding in terms of emerging technologies. These information are quite useful in terms of handling the different types of traffic for different scenarios. And multicast versus unicast security comparison was there on one of the slides, and we discussed details like usually the unicast traffic. If you want to send unicast traffic in a reliable way, we are using TCP transmission control protocol, and it has quite uh, handling of three-way handshaking and all those things. So reliability handling by the TCP protocol design. But there is another protocol which can you can consider using it for unicast as well as multicast. That's UDP, unreliable datagram protocol. And most of the multicast implementations are based on the UDP. It's the behavior is somewhat different in terms of its implementation and how the applications behave. And then we discussed on another aspect, the per application state. The multicast usually quite optimal in terms of if you're limiting the resources, so optimizing the resources on your systems and the network. Then unicast is quite useful in terms of one-to-one communication. But if you are doing one-to-many communications or the many-to-many communications, then usually the multicast is better in terms of optimizing the computing resources and the network resources. And then we had a discussion on the brief history of multicast. I mentioned that 50 years back, we were having TCP/IP protocol stack. I think last year they celebrated, last year or a couple of years back, they celebrated on the 50 years of TCP/IP stack. But even though those implementations on 1970s until 1985, there is no formalization in terms of multicast applications or handling. The first standardization started on 1985, and the basis of the standardization there onwards evolved over the several steps. This is the first step in terms of the implementation of multicast standardized protocols or standardization process. Okay, then the next iteration of standardization initiated with the RFC request for commons 1075, and it's on 1988. I discussed on the assumptions there, and then I went into the details of multicast routing aspect, which is based on the protocol name protocol independent multicast. In there, that doesn't mean the multicast implementation is totally independent from unicast or vice versa. what does it mean is the independent is irrespective of the it's dependent on the unicast protocol. The multicast to be work, multicast routing to be work, you need your unicast routing to be function well. So it's one of the main aspects in terms of troubleshooting. Before you start troubleshooting multicast routing or the multicast traffic routing, you need to check your unicast routing tables or the unicast functionality end to end. Then only you need to consider in terms of further troubleshooting on the multicast routing, because the multicast routing running on top of unicast routing. So that's one of the important aspect in terms of protocol independent multicast, mainly useful in terms of multicast routing stuff. The first couple of protocols implemented based on the multicast, something called multicast dense mode, based on a standardization of RFC 3973. This was quite useful in the early days, but nowadays we are mostly dependent on something called multicast sparse mode. We will be discussing the details today. What's in terms of the multicast routing aspect, which means layer 3 multicast. And there is something called rendezvous point, which we call RP, and that is something implemented with the sparse mode. The multicast, the dense mode, protocol independent multicast dense mode usually doesn't require intermediary or central point to communicate sources to communicate with the receivers. But rendezvous point implementation required in terms of protocol independent multicast as an intermediary point between sources and the receivers of multicast domain. So we will be discussing the details. Just wanted to give you a understanding on the key topics or key areas of concern when we are learning. And then I was discussing on the domain, the applications as well, in terms of most of the time we are concerned of the one-to-many applications, which is quite famous in these days, especially in terms of IPTV applications like the Sri Lanka Telecom, the POTV application usually based on this ideas such as one-to-many implementations of multicast. If you check or if you were able to capture the traffic from your local POTV network, probably you can find out there are lots of multicast communication going on there. You have the SLT data centers maybe, or data centers may be having streaming servers. Those are the senders. And if you are listening to all the live broadcasts sending from the different servers and sending to different multicast groups, or we can discuss further options as well. And when you are changing the channels, what you are doing is usually you are changing the multicast IP group or IP multicast channel. So that's quite famous in these days. There is something called a modern evolution called the protocol named initially we discussed on the dense mode, PIM dense mode, PIM sparse mode. There is another thing implemented to further optimize the multicast flow, which is based on the RFs, the couple of RFCs, and identified as source specific multicast. So we'll be discussing the details today. And it simplifies most of the stuff, and it's more if you need to consider implementation with a secure fashion, then this source specific multicast is much better, or much better alternative in terms of security compared to the source PIM sparse mode general implementation. So if you are recommending somebody to implement multicast at the first time or upgrading the multicast network, probably you can consider advising as a security expert in terms of implementation of source specific multicast. that is mainly targeting the implementations of one-to-many applications. These were some of the applications I was discussing. We had discussion on e-learning applications and the stock exchanges for the market data distribution, and the security surveillance probably have implementations on multicast, especially on the large metro CCTV environments. Without flooding the metro networks, you can use the multicast technologies to optimize the monitoring of entire city. And the video conferencing definitely getting in all the multicast for the optimizations. And there are more applications such as for enterprise applications, such as your CEO. If you are in a multinational company, if your CEO wanted to address you with your quarterly results, then that can be done through the enterprise network by implementing multicast without flooding entire network, by creating unicast sessions for each receivers. And the healthcare is somewhat useful in there if multiple doctors, multiple doctors from different geography is joining for the healthcare sessions or probably the operations. This will be a better alternative rather than flooding your network and the missing the communication in there. And the retail catalog distribution, like large supermarkets can be use this particular mechanism to catalog upgrades, frequent catalog upgrades to entire supermarket chain of branch chain or the branches from the head office. And software distribution again, it's quite useful in terms of if you have many large millions of end devices or the large number of branches, probably you can use multicast to patch updates for all the servers in the branches from the head office. It's quite useful in terms of rather than flooding your network in a patch update at the same time. So not only the enterprises, there are several use cases in the data centers as well. So modern data centers having these implementations for the control planes or the controlling of traffic, for the creating the fabric of servers or fabric of equipment. So probably these are some of the examples of usefulness in the data center for the multicast technologies. And we discussed on other options as well. And it's quite useful in terms of scalability perspective, because your network can be scaled with many number of receivers, because increasing number of receivers from multicast perspective not required more bandwidth, because it's optimized its own way. The resource utilization will be reduced by replacing unicast usage for certain applications. And the performance will be better because it's not flooding your network, and you are just route replicating one message, and number of subscribers doesn't impact in terms of performance. But for unicast applications, if number of receivers getting increased, then you need to scale your network, or you need to your performance will be dictated if you haven't addressed. But in case of multicast applications, number of receivers getting increased, not impacting the overall performance. And then I categorized the multicast applications to 3 different types: the one-to-many, many-to-many, the many-to-one. Usually, the most famous one in terms of applications is one-to-many, which means one sender and many receivers. And there are applications like the many-to-many, which means there are many senders and many receivers. So that's usually in terms of there are applications like if you're doing video conferencing, that's a many to many communications, because you need to send, you need to send video and receive video at the same time. So that's if we have a multi-party conference, a video conference, then at the same time each participant will be sender and receiver at the same time. So that's the kind of many-to-many application example. And there are many-to-one examples, like if like in the previous situation, if you have a large number of CCTV cameras, and if you are sending your recordings to one single server, then that's something many to one communication. And if you are doing sending resources to one single entity from a multiple sources, then that's many to one. The receiving side will be usually a storage or kind of a central server, and many senders are there in terms of the applications like CCTV. Then these are few fundamentals on the multicast. And I just need to highlight one more thing I forgot to tell you initially. These topics are advanced topic. Now you are on 4th semester. Probably some of these topics may not able to, it's better to communicate with other colleagues. It is difficult to recover back if you have not attended these next few lectures, because these are some advanced topics, and the fourth semester topics, not like introduction to networking. And these are quite useful. And in terms of your assignments, the first 6 sessions you got assignments with the most of the basic troubleshooting stuff, which any network engineer or the colleague with the network exposure can help you to understand at a later stage. But these topics, what we started from the session 8 on the last week, session 7 from the last week, it's quite advanced, and troubleshooting aspects are somewhat different. These may not, these topics may be not able to covered by the fresh network engineer or people who don't have the deep dives in there. It's quite important to join these the lecture sessions if you are planning to get the A or A plus kind of a score in your this course module. If you have any questions, just you can ask anytime in terms of unmuting or typing the question on the chat. Probably you can send a message as well. Okay, let's go back to the multicast considerations. There are few rule of thumb, so you need to, these are the considerations in terms of implementing multicast applications or the configurations or the troubleshooting. You need to have these ideas, especially in your mind. The first, there are 5 major considerations. First one is UDP. Multicast is mainly UDP based. So unreliable datagram protocol, it is not mainly based on TCP, which is famous, which is the reliable protocol from the TCP stack in terms of transport layer. So if you are using UDP, then it is not connection oriented. Okay, like in the TCP IP, there is no handshaking, just sending from source to receiver. No verification before sending, no 3-way handshaking. So it's mainly UDP based. That's why we started I put the topic, the course topic as the IP multicast. So it's based on TCP IP stack, and the layer 3 protocol is IP. It's based on internet protocol. So so the transport layer mostly will be the network layer is still IP, but the transport layer mainly based on UDP for most of the applications. And best effort delivery. So that means multicast. In a multicast network, you need to assume that there can be drops. So you need to plan your applications according to that, with assuming these multicast implementation technologies are quite useful, but most of the default implementations, you need to expect drops there. So accordingly, your application must have a resiliency for the drops. So especially most of these applications selected with assuming the occasional drops there. There are research going on, especially on the reliable multicast, which these are few of the protocols developed there. There is a protocol named the PGM, FEC, and the QoS is something quality of service implementation for the prioritization of traffic. We are not covering details on this, but just for your sake of understanding, there are efforts or research going on improving the reliability of multicast to reduce number of drafts in applications. It can be implemented by applications for the recovery. If any of the packets lost, you can put a unicast channel to get it back from the sender. Those implementations are available, especially on the market data recovery on the stock exchanges, as well as there are other applications as well. So these are few of the modern evolutions in terms of the recovery of traffic. So that's the drops are expected there on the second point. No congestion avoidance. Usually TCP IP implementations, they have a implementation to TCP/IP stack implemented on operating systems by using TCP windowing and slow start mechanisms to avoid the congestions, but there is no congestion avoidance mechanism by default for the multicast implementations or the usual default protocols. And that should be addressed, because if there is no congestion avoidance mechanism, then that's something you need to consider when you're selecting the applications or implementing applications. Then there can be duplicate messages, which means source will be sending message to the multicast group or intending to receivers who are expecting to get the message. But there can be duplicates based on the tree structure built to deliver the message. So that's something you need to consider. Duplicates should be expected, and your applications need to have the consideration on this to avoid or drop the duplicates. And the fifth one is out of order deliveries can be expected, because there can be situations the first packet may come later after the second packet or something like that. So out of order delivery must be expected, especially on the multicast consideration. These are the considerations you need to have when you are selecting or migrating applications to multicast. The fundamental we discussed this unicast as multicast, but in terms of addressing schemes, usually multicast sending a message to each and every receiver by addressing the receiving address, or receiving IP address or receiving MAC address. But in terms of multicast, it doesn't send packets to each and every receiver. It's just sending or multicast source. So the streaming server sending messages just to the virtual group. So it will be replicated and delivered to intended receivers. So it's not addressing each and every destination, but sending to a general group address and receivers will be picking it up based on by using the tree structure built by multicast control plane. So same packet will be delivered to all the receivers. But for unicast, each and every one getting a different message. So that's one of the fundamental differences. And so this is the idea we discussed previously as well. So source will be sending multicast, source having unicast address, and it's sending to the multicast receive address as a multicast group IP address range, and then all the subscribers who are intended to receive the group multicast message from a particular group will be getting the message. So that's something. And then we discussed on the multicast components. Within this course module, we are discussing only the campus multicast. There are the multicast technologies for the ISP level and as well as interdomain multicast. We will be not discussing details on that, but I just wanted to put the slides to make you understand the scope of scope of this particular course module for at least for the multicast. And the most of the multicast on the campus model marked here by the orange at the left bottom. You can see that IGMP is one of the protocol implemented there, and another one is any source multicast, which means protocol independent multicast basically. So campus multicast will be the coverage of this particular course. The other areas will not cover due to the time constraints. Okay, then we had a chat on the multicast IP addressing, what we have discussed in these slides as well, extension of this slide. So multicast have separate group addressing range, which means 224 0.0.02 239 255 255 224 to up to 240 will be the class D address range. Class A means your first octet will be entirely utilized the reserved, and last three are the host addresses. Like the 10 dot range usually comes under the class A. I think those the protocol details and everything covered on the first semester course, which is MC4004. And the class B is usually like 172 range, and the first two octets will be used for the network portion. The class C is first three octets like 192 to 168 range, which is for the first three octets representing the network address. So multicast having the different IP range, which is the class D IP range 224 from 239. So this source address can never be class D multicast group address. You can see on the previous slide as well. When put source address is usually a unicast address. It will never be a multicast address. The multicast address can be only a destination address. So that's usually, it's important. You can't configure a multicast range on any of the interfaces of your servers or the network equipment interfaces. It will never be interface address. So you can't have multicast address as a source. Usually multicast is a destination group address. So the short way of representing the group address 224/4. If we're adding routes, you can do that by using the short form of adding 224/4. I will create a lab lab sheet, and probably you'll be getting chance to do the labbing with the instructor. I'll be forwarding that to Dr. Tarindu, and probably he'll be arranging instructor sessions later for your practicals. Okay, then another fundamental is the multicast group address are not in the unicast routing table. So network equipments usually have the unicast routing table, and multicast works on top of unicast routing table. I previously mentioned that there is a dependency there, but irrespective of the types of unicast protocol, it's named as protocol independent multicast for the multicast protocols, protocol multicast routing. Still, the network devices have separate routing table for unicast and separate routing table for multicast. When you're troubleshooting, you need to have this understanding. But operating systems does not have separate routing table for unicast and multicast. Let me share a few of the command line interface. Just give me a second. Hope you can see my screen, right?
Yes, sir.
Okay. All right. If you want to check in terms of you can see this, use this command, route print on Microsoft operating systems. Okay. When you check this, you get two routing tables, IP version 4 routing table and IP version 6 routing tables. We are not covering IP version 6 because it's beyond the scope of this particular course. And IP version 4 routing table inspection is sufficient enough for our learning here. Let me filter it out. You can filter it by putting a /-4. So basically, this is an example of the Microsoft Windows routing table, which is an operating system. So you can see both unicast and multicast routes are there, even the broadcast included there. You can see that 127 range route is there. That is your loopback, local loopback. And you can see that that loopback range address, and then the first IP range address 127.0.0.1, that is again unicast, which is the host IP host local loopback IP address, and then still it's routing to the virtual interface from 127.0.0.1. And you have the 127 subnet broadcast address, which means 127.255.255. And it's again addressing or forwarding to the interface of 127.0.0.1. So likewise, in this particular, in my network interface, IP address is 192.168.1.29. And 192.168.1.0 is the range of IP address. You can see that subnet mask is 255.255.255, and the host portion is 29, the last octet. And you have a subnet broadcast address with last octet on 2.5. And then you can see that the multicast range included here. The 224.0.0 is the multicast IP address range. if there is a multicast sending from this particular host, it will be forwarding to either loopback, both loopback address. If there is a service who is receiving on the same host, that will be forward to the loopback, which is the local loopback, and additionally it will forward to the my network interface, so which is connecting to the default gateway, which means 224.0.0 with a subnet mask of 240, which is /4, which means first 4 bits are one, all in one. That's the network portion for the multicast address range. And this will, any multicast traffic will forward to both local loopback for the local applications, and the external receivers, it will forward to the sending interface. In this case, 192.168.1.29 is my interface connected to the local area network. And there are two other routes which are broadcast. You can see, you can identify broadcast by if all of your bits are one, which means 255, 255, 255, then it's a broadcast. That's the broadcast route. You can see on top of that, there is a default route. That is your default gateway. If you are sending traffic outside of this particular network, which is 192.168.1.0, if you are sending traffic to anything other than this, represented on this router, this routing table, it will definitely send to the default gateway. The gateway address is 192.168.1.1. That's my router on the VLAN, or layer 3 interface on the VLAN. So that will forward through the network interface, which is having configured IP address of 192.168.1.29. So this is something you can see that all the unicast and multicast routes are on the same table. So that's usually the behavior for the all operating systems, including Linux as well. But for the network equipments like routers and the switches, you see the separate table for the unicast and separate table for the multicast. Even when you are configuring a router or the layer 3 switch, you need to enable the multicast routing separately. By default, it's most of the time it's disabled. If you are configuring multicast, by default, it's only available or up and running or available with unicast. Then you need to specially enable the multicast routing by a separate command, or so that's the usual way. And then thereafter, network device will maintain separate routing table for unicast, separate routing table for multicast. Right. And I added a couple of slides on the last lecture, which we discussed previously. If you are troubleshooting on your host, you can see that you can use address resolution protocol, ARP table on your host, which is mapping your MAC addresses with the IP addresses on your local network. Similarly, you can see the multicast. There are some MAC address to multicast mappings by default. Even if you are not using multicast, these are by default available in your ARP tables. You can see that the 224.0.0.2 is a reserved one, and with a MAC address of 01005E. You can see another address which is ending 22, also having a MAC address mapping, and two of others as well. There is you can see that all four multicast entries, and there is another one as well, 239.255. It's another multicast, and the last one is the broadcast address, having all 25 for all the octant, and the MAC address with all F, which is hexadecimal. And you can see that multicast address range starting from 225 up to the 239, having the entries with the MAC address entries with the 01005E, which is common to all multicast IP addresses mapping to the physical address. See, first three the octane. So first three hexadecimal places 0100 and 5 common to all the multicast addresses. So this is something interesting, something important to know, that even though multicast I group address is a virtual, it's having a physical address or the MAC media access control MAC address for each and every multicast. There is a complexity as well with that we can discuss later. So you can see the differences. Unicast addresses starting from 192.168, all the 168.1.1 and 1.24, which is not the host mapping, and all having different physical addresses. But again, on the subnet broadcast, which is 192.168.1.2255. If your network want to, if any of your hosts want to send broadcast only to your subnet, then you can address by using this 192.168.1.255, and MAC address will be OLF in their all the 6 hexadecimal places. Similarly, if you're sending full broadcast, then you are sending with the all 255 on 4 octans, and all are representing the they are on the all hexadecimal places. So these are by default in ARPs on your table, other than the dynamic ones, which created later with the default gateway 192.168.1.1 and another hosting my network, which is 1.24. The other things are by default enabled and mapped and reserved. We'll discuss reserve multicast IP addresses later. I think last week I discussed some of them. And then what else? So I mentioned, we discussed this IP config all option. If you are interested of knowing the details on your local area and your local computer network interface cards and the addresses, in this case, I have Ethernet adapter connected with RJ45 as well as Wi-Fi adapters configured there. You can see the details there. We discussed this, the settings on one of the previous lectures. Okay, let's go back to the recap on the lectures. Okay. So I just wanted to highlight the point here on the separate routing table is maintained for the active multicast routing entries. Just give me a second. Separate multicast group address will be there. Multicast group addresses are not in the unicast routing table for network devices, but not for the case of host devices, which means operating systems. A separate table is maintained for active multicast trees in the network. That's the tree building process we will be learning today. And it's maintaining a separate table for the active multicast trees in the network. And the multicast state entries are initiated because this multicast joining process is somewhat dynamic, and it's the routers and the network devices are maintaining, even the Windows maintaining uh, the state table, whether somebody wanted multicast at this point or just wanted to leave the multicast is receiving, then that need to be updated somewhere. So usually state tables are maintained like similar to the firewalls in terms of multicast states. The sources, I hope you can recall that switches usually doesn't maintain state tables other than the MAC address tables for the mapping of switch ports. with the MAC addresses. The routers usually maintain state table entries. The firewalls maintaining state table entries for. So other than that, switchers usually does not maintain state table entries for each and every session. The sources do not need to join. They just if you are sending message sources, you usually there is no requirement to join. The receivers are only the one who need to signal whether they prefer to listen to the multicast group address or not. The sources just sending messages to the destination multicast address is sufficient. You don't need to join the network or multicast network to send traffic. That's one of the important points. And the multicast routing protocols build and maintain tree hop by hop based on the receiver membership. So receivers are signaling their memberships to the group, and the reachability to source will be achieved by this tree architecture or tree building process. The source reachability is derived from the unicast routing table. That's why I mentioned you need multicast to work, you need unicast routing to be function. To find the source, you need the unicast routing established before you proceed with the multicast functionalities. And these are the multicast addressing again. I hope you remember that 224.0.0.2 was there on our routing table and my local host, and it is a reserve address. If you are communicating with all the hosts in the all the routers in the subnet, then this is the multicast group we are using from real using for the VLAN communication or the local area network communication for the to communicate with the between the all the routers. If you 224.0.0.1 is another reserve address, which is having which is again if you are communicating with your own subnet of devices, including the computers as well as the routers, then this is the address. So there are other reserved addresses for different protocols like OSPF is a routing protocol. And you can't use this for your application multicast traffic because these are reserve addresses. Therefore, you need to know what are the reserve addresses before you are enabling that to be used on your multicast applications. And but there is another the note on this. This particular range is only reserved for particular or only applicable only within your subnet or VLAN, usually mapping to the subnet. So it doesn't go beyond your broadcast domain, which means the first stop router, which means your default gateway. It doesn't go beyond your default gateway. That's by using a TTL field name, TTL field in your TCP IP stack or IP stack. That's called time to live. So once any of these addresses or packets addressed to these IP addresses, it will not go beyond the first of router, which is the default gateway. Usually those are reserved only for the first your network segment or the subnet range. That's why it's mentioned as TTL equal 1. It doesn't go beyond the first router. Likewise, how we discussed on the trace route. So TTL will be used here for this to restrict the boundary of the multicast traffic. And other reserve addresses are there. Some of these are mentioned here. You know that we will be discussing the time synchronization, and there's a protocol named Network Time Protocol on the next one of the next sessions. And it has a reserved multicast range to synchronize the time between the servers and clients. And there are a few other applications which are famous on the financial markets, which is again reserved for few applications. You can't use this for your application. And there is a special range. You can see, hope you remember when I will include that on lecture slides, appendix as well. There is a private multicast range, likewise in the 10.172 and 192 range on your unicast multicast ranges, which are not available on the internet. As that private IP range for the multicast is 239 /8, which means 239.0.02, 239.255.255. These multicast ranges are quite useful in your internal implementations because those are not available on the internet, and this is reserved for private use. If you have applications deployed, multicast applications deployed internally only, then you can use this particular range. The GLOP is another range developed for the research and research stuff, and it's not any more useful or discussed in the field. But just giving you these addresses for the reservation, then you are quite knowing that what are the ranges available for your daily usage. There is another specific range assigned for the source specific multicast, as we discussed before. That's 232. So just wanted to highlight you are quite useful, quite okay to use 239 range since it's private IP range. That's important. And lastly, on the last week, these are the last two slides I discussed. We'll be starting again from this point onwards. This is the service model of multicast as an overview. So you can see that all the steps based on the separation of segments. You can see on the right side, there is a multicast source. So multicast sender, and source is sending multicast stream A traffic to a multicast group, and the first of router getting the multicast stream from the source, because you don't need to join sources to send multicast. Just sending it to your default gateway or the first of router is fine. Then there are still the first of router unable to send it to the if the source started first, it doesn't allow to send to the next routers or the downstream. So you need to have a request from the receiver side to send traffic from the first of router. That's the difference between unicast and multicast, as we discussed initially. The second process, you need to even the sending server or the sender can keep on sending the messages, but receiver is not getting it. Receivers need to subscribe to receive the message from this particular group or channel. Then the receiver on the left side, you can see that receiver signaling that I want to receive stream A, and sending a signal by use to the last of router in terms of their first of router by using a host router signaling protocol. That's via the switch. Then the router will take the request and forward use another protocol, which is router to router communication. The previously signal sent from the receiver to the first of router or the last of router in terms of other perspective through the switch by using this blue color host to router signaling protocol I marked by dotted line arrow. Then the first of the receiver side first of router will be sending a router to router signaling to the next of router with a request. That is by using protocol independent multicast, which is multicast routing. So the layer 3 multicast. So then the next of router will send based on the unicast routing table to the the first of router from the source perspective. Then the first of router will start sending the message. You can see it marked by red arrow on an opposite direction which the request coming from. You can see that traffic goes the opposite direction from where the receiver sending a request message or subscribing message to the first hop router or towards the source. So it is the beauty in terms of multicast. Usually the signaling works. So the control plane of multicast works and sending traffic from receiver to source direction, right? Usually the unicast traffic just sending traffic from source to the destination. In this case, the signaling goes from receiver to source and the traffic goes from source to receiver. It's still similar to the unicast, but control plane, the data goes through, still goes through from source to destination, but the receiver signaling they are intended to receive the multicast should go the opposite side. So that's the difference. And if we segment these requirements, segment these traffic paths, you can see that the source network is there, and then the routing network will be there for the layer 3 network. And the layer 2, the switch between the members and the receiver members, or the receivers and the first hop router in the default gateway router connected through a switch. That's the layer 2 network. So we'll be discussing this layer 2 multicast and as well as layer 3 multicast in details. And these are the important points we will be testing on the assignments as well as the final examinations in terms of the multicast, mostly based on layer 2 multicast and layer 3 multicast in terms of questioning. And the last slide on the last week. So I took more time to explain this because can't proceed without the fundamentals in terms of multicast troubleshooting. IP multicast usually having IP multicast sources are having unicast IP address. Any device any source or any device sending an IP packet address between 224.0.0 to 239.255.255. That's the multicast source. Multicast source must be having unicast address, but its destination address, if it is sending to the multicast channel or the stream, then it should address within this particular IP address range. A device can be multicast sender and multicast receiver at the same time. I mentioned you that the video conferencing, usually you are sharing your video and you are receiving others' video as well. So in that time, the multicast sending and multicast receiving at the same time for single user or single participant possible at the same time. It doesn't mean multicast. So most of the situations, but multicast senders are just sending and receivers are just receiving. But it's not. It's also possible to send multicast and receive multicast at the same time, which means send and receive functionality can be overlapped on a same host. There are no multicast control traffic between sender and the network or between the sender and the receiver. So usually the multicast signaling goes with the receiver to the router, first hop router or via a switch, but control plane traffic not goes to the source. It ends up the first hop router mentioned here, but it not going towards the first hop router to the source and ending at that point and handled by that. So that's the reason, one of the reasons why the multicast sources does not have a requirement to join the multicast group, especially by signaling it. So only signaling goes from receiver to the source direction until up to the first hop router. So there is a question we discussed on the last week. So how does the source know when to send a traffic? An application tells the source to start transmitting. So basically, source will be sending traffic, and the receivers just need to join by signaling and get the message. So source does not require to know whether the receivers are listening or not. It's not necessary. You're just delivering the message or start sending the channel message, and receivers required to join to get the message. Okay, these are some of the reference book I included with some of the URLs which can be useful on your further reading and understanding if you are interested to deep dive. So the first couple of books are quite famous in terms of top-down network architecture. It has a separate section for the multicast, and another book which is from the Tannenbaum. You can see there is a multicast section there as well. If you are deep diving and interested in knowing more further on troubleshooting and implementation, there are 3 big books from Cisco Systems. You can go ahead and learn from these 3 books as well in terms of your reference. Okay, further, I included a couple of outputs to make you remind in terms of your the previous understanding of ARP tables and the configurations of devices. I will include another slide on today's lecture on the routes as well. And further, I included appendix on your first semester course on network design for a recap in terms of the simple host-to-host network to up to the functionality of a hub, and then evolution, the advancement up to the switch, and limiting the broadcasting domains. All those functions are there. And default gateway functionality, which is inter-VLAN routing or inter-subnet routing. And I included a bit of details in terms of multi-layer switching. So including here, I just need to remind you in terms of if you have a switch with 3 different departments, so 3 different VLANs created for them, need to intercommunicate. You need to have a inter-VLAN router put on there and have each VLAN segment need to be connected with a router interface on a traditional way, but later there is an emergence on the trunk link which can configure and carry different VLAN traffic by using a single physical cable. So you don't need 3 different interfaces and cables to route between 3 different VLANs or subnets. Then the multi-layer switches emerged with the layer 2 ASIC and the switch processor and the route processor integrated together in a one device. So you can communicate between the 3 different VLANs by using multi-layer switch. That's a fundamental, should be covered on the first semester course. And if you are communicating between different VLANs, this is the way, and 2 different subnets highlighted here, 192.168.10 range and 192.168.20 range. So these are the fundamentals of unicast on your first semester. So these ideas need to be keep in mind, because you are separating, by creating VLAN, you are separating the broadcast domains. So including the multicast domains as well. If you are separating VLANs, then you need to, if you are communicating through the multicast, you need to have a multicast routing function implemented on this multi-layer switch or the router in between. Okay, that's about the recap on the last section, because quite important. Otherwise, you can't move ahead with the troubleshooting stuff in terms of multicast. So we'll be starting some troubleshooting stuff on today. Any questions until this point? Okay, so this is what we covered on the last week. the highlighted by green color. And I am starting on the layer 2 multicast and the layer 3 multicast today to complete the IP multicast fundamentals. Then we can go ahead on the IP multicast troubleshooting section thereafter. So the last week again we discussed on the same slide, and we segmented layer 2 multicast and layer 3 multicast and source network and the member host or source host. So then this is the slide what we discussed on the addressing scheme. So let's start from on the layer 2 multicast segmentation here. So layer 2 multicast basically, so you can see the segmentation here again. There are members or the multicast receivers or the endos there. And then you have layer 2 network, which included the switch up to the first router interface. And after the first router interface, there will be several other intermediate routers, and the first of router which is connected to the segment of the host source streaming host or source server, multicast source or channel server. So they are from source starting to send multicast stream to let's say multicast stream A is sending to the first of router. So this is the state right now. So now the receivers need to signal the interest to receive stream A from the source A. So how does it done? It's by using, so it has an intention to receive stream A. Let's say the CEO addressing the multinational company CEO addressing entire all the employees. So employees now on their computers, and so you are marked with the streaming URL, and you need to join by using a streaming application or receiving application for the stream A. And your CEO CEO started the speech from their side. Now it's sending through the source server, which is source server, and sending a stream to the first of router. Now the receivers are joining with their receiving application for the to listen and or watch multicast stream A, to then to listen the message from the CEO. Then the endorsed or the receiver host must send a signal to the first of router or the last of router in source perspective, but the endorsed perspective, it's the first of router sending a signal by using a protocol host to router signaling protocol. For the multicast, that protocol name is IGMP. Okay, that IGMP protocol is the layer 2 net multicast routing multicast signaling protocol. So that's the interest on our discussion on this particular segment. So how this IGMP protocol works and the functionality that need to be learned in this section. So host to router signaling protocol, IGMP will be the focus point here. Then we will be discussing the layer 3 net multicast as well. Then router to router signaling protocol will be discussed thereafter. So let's start on the IGMP. This IGMP is host to router signaling protocol to receive the multicast from the first of the immediate default gateway route. Then the protocol named as Internet Group Management Protocol. The short name is IGMP. That is usually initiated or used by a host, not by the source or the intermediary router. It's only the signaling from the receiver or endorsed to the immediate default gateway or the local router to notify the use by the local host host to notify the local router that it wishes to receive or stop receiving multicast traffic for given destination address or group, which is if you are not if you are interested to receive traffic from a multicast group, then this protocol will be used to signal the requirement to the local router or immediate router. Then once you are receiving it, if there is no requirement to receive any further, then same protocol can be used to signal just stop this the channel delivering of this channel, then it will stop from the first of router or the local router, and it will not send to the particular host. So it will not require to waste the bandwidth, keep on sending. So you can use this signal any host to request traffic or stop the traffic from multicast group. And there is a standardization for this particular protocol. There are 3 variants of IGMP. The first variant is IGMP version 1. Currently most of the enterprises using IGMP version 2 because IGMP version 2 have more features than 1. Like IGMP 2 has something called the leaving message implementation of exiting from receiving the group included with the IGMP version 2. The standard is RFC 2236 from IETF, which is called request for comments for the standardization initiation. And there is a new evolution. Actually, it's not new, but it's still it's kind of an emerging implementation. The RFC 33376 is a protocol name, protocol specified for better IGMP signaling approach, which we can discuss later. IGMP version 3 is identified this way. So there are 3 versions, version 1, 2, and 3. So good network support, but host implementation is still patchy because you need to invest time on implementing these version 3 features. So still the industry is most famous among the version 2. Okay, let me go ahead with a step-by-step approach how this IGMP version 2 works. So there are several slides for this, but just simulating the step-by-step approach. You don't have to worry on the number of slides, but just giving you an impression how this is working. So IGMP version 2, we're trying now this endorsed is starting the signaling process by using IGMP. So this will be the process now. So you can see that end host is there who is intended to receive traffic. It immediately connected to the switch, and that switch has 2 other hosts connected. And another host is there who is intended to receive, that's named as receiver 2, which are both of these machines, receiver 1 and receiver 2, installed with the multicast application, receiving application. And there is another computer connected to the same switch. It doesn't have implemented or installed the multicast receiving application. So there is no intention to receive multicast from there. So they don't have interest to join the multicast stream to receive it. And then our switch connected to the local network router, which is the first of router in their perspective. And it is having the Ethernet IP address of 10.1.1.254, which is the interface connected to the switch having IP address, this particular 10.1.1.254 IP address. That's the default gateway of all these hosts connecting to our switch. If you are sending traffic to anything beyond your VLAN or the subnet, then you need to send your default gateway. The default gateway is the hop first of router Ethernet 0 address 10.1.0.254. Any questions until this point? Because before we move ahead. Okay, now you can see the unicast addresses. So the first receiver having the local IP address in the network card connected to the switch, or the switch is having Ethernet 0, 10.1.1. And there is another intended receiver. Its Ethernet network card address is 10.1.1.2. That's there. It's those are the two IP addresses of those two hosts and their network cards configured according. And there is an unreceiver, the IP address not highlighted here. There is no requirement to raise forward multicast traffic to this one. So now you are planning to receive multicast, which is coming from the source network, source side, and it's capable of coming up to the last of router. Now you are signaling the requirement. Receiver 1 signaling the requirement. I want to receive group 234 1.1, which is coming as the multicast stream from the upstream routers. Now, the first router has a signaling now signal by using its multicast receiving application. Then the TCP/IP stack or the IGMP protocol included there on the host TCP/IP stack included this IGMP protocol on the host operating system, a network stack. And it's sending IGMP membership report marked by dotted line to the first the switch up to the switch. So it having the contents of IGMP membership report having the requested group. You are requesting to join the multicast group or channel 234 1.1 IP allocation, which is the allocated IP address for the multicast group, which is receiving from the upstream routers. And then your source address is the IP address of the receiver, 10.1.1, which is the receiver one. And destination is 224.0.0.1. Hope you can remember this IP address I mentioned on the last week, which is a reserved address. Let me go up to that particular slide. So there is a reserve address 224.0.0.1, which is addressing all systems on your subnet. And there is another address again, which is addressing 224.0.0.2 all routers on the same subnet, this subnet. So now you can see that this is not this signaling sent not to this particular unicast address of the router, but it's sending to 224.0.0.1, which is all the other hosts and the routers can hear this message. That's why by default this address is allocated and configured on all your operating systems to support multicast. Now it's going from the receiver 1 to the switch. But switch doesn't handle IP protocol, right? It's a layer 2 device. It will just pass through usually the multicast traffic, this reserve address addressing everybody in the network, which means other receivers as well as all the non-receivers, and it's definitely forwarding to the first of router. And you can see that switch to router, there is another dotted line with the arrow. So switch will forward it to the first of router, and the router will be knowing that there is a request from one user or one receiver for this particular 234 1.1 multicast group, which is requesting multicast feed from upstream. Now, second step, is the router will immediately start forwarding the multicast traffic to the switch based on the request. And before that, even though it's receiving the first of router receiving traffic, multicast traffic from the upstream router, it does not forwarding. But once the first receiver made a request, it start forwarding it to the switch. And switch will forward that traffic to the receiver 1. Then receiver 2 again wanted to have thereafter wanted to have this same join the same multicast group to have the traffic listen to the feed. Then it will signal by using the IGMP protocol. Then switch will not forward the additional reports to that, because switch already know that there is one user here. I just need to forward the traffic to the second receiver connected to its own switch. So that's important, right? Otherwise, unnecessary signaling, duplicate signaling again to the router. Rather than signaling again to the router, they'll just forward the traffic to the second user by duplicating the traffic or forwarding the traffic. Same traffic it's receiving from the router. So likewise, it will be forwarding. Now, then the IGMP, the message, you can see another highlight here. The source IP address, you can see that the IGMP message does not include the identity of the multicast source, because it doesn't have understanding of the multicast source, because multicast source not defined, only requesting traffic from the particular multicast group. There is no requirement to know the source IP address of the multicast. Let me go back. So you can see the source already sending. Multicast receivers does not have a requirement to know the IP address of source, something like unicast communication. But for the multicast, you just need to join the group address of multicast. So you don't need the unicast IP address of the source. Just you understand, knowing the group address, it's enough to join the network and receive the message multicast stream. So it is important again. So then I'm just explaining from the IGMP version 2 perspective, because it's more clearer, because that's the usual the industrial best practice or the usual practice in terms of implementation. So then let's move ahead. That's the joining process. If one join, another one can join from the same switch connected or same VLAN or the same LAN segment. Switch doesn't have to send another report to the IGMP or the first stop router, still duplicating the message and sending to the second receiver only. And it's more optimized, right? So now suddenly, now both of the receivers are getting the message, getting the multicast feed, and suddenly the receiver 2 want to exit from the, or just I don't signaling that I don't require this stream anymore. So it's moving to another work on this host, and receiver 2 signaling to signaling that it's not required to receive this stream anymore. And you can see that non-receiver not getting the message as well in the same scenario, because it doesn't requested, or the multicast application not receiver application not installed there. And now the receiver 2 sending a leave message. The IGMP version 2 implemented with this leave message. IGMP version 1 does not have this implementation of leaving mechanism. It's just joining mechanism implemented with the IGMP version 1. Later, people understood that the engineers, the designers understood that we need to implement something for the exiting or leaving the multicast listening by using listening as well. So that's why IGMP version 2 implemented it's having IGMP leave message. The leave message sent then sent by the receiver to exit from the group, and the leave you need to in the leave message you need to mention the specific group which you are exiting. If you are listening another group, you are not exiting from that. You are exiting from this particular 234.1.1 group. And the source IP address need to be its own IP address, which you are saying that the request is I'm sending this reserve the leave request. My IP address is 10.1.1.2, which is the network interface card or host IP address there on the receiver too. And the destination, again, you can see that it's the 224.0.0.1, not the group address which you are exiting, but you are sending message to the reserve IP address, reserve multicast IP address, which is addressing your router and the other host here. So router is getting that particular message, leave message, and it's again going through the switch. Then after that, router started following up, just checking are there any other listeners here or other receivers here before stopping the stream, because there can be other receivers who hasn't signaled or automatically disconnected, and at least one receiver must be here and respond if it's required. So now router started sending IGMP group membership query message based on the leave request by the receiver too. Now it's sending back to the switch, and then you can see that switch will forward that to the receiver one, and receiver one, because receiver 2 already signal I just need to exit, so it will not respond. But receiver 2, since it's already listening, it will signal with another membership report saying that yes, I need to listen to this. I still need this 234.1.1, and you can see that it's sending only to the router. 224.0.0 is the just addressing the routers. 224.0.01 addressing entire all the host and routers, because everyone in this network will be hearing this. When you're addressing 224.0.1, it will not go beyond the first router, because I mentioned that this 224 and 224.0.01 and 224.0.022 are only within the segment, which is the TTL equal 1, right? You can see that this one, the receiver one, just make you a reminder on okay. You can see that I mentioned you that 224.0.01 addressing all the systems on the subnet, which means host and the routers. 224.0.0.2, which is the reserve address for communication between all the routers. That's why the receiver one only sending the still I need this multicast feed, signaling only to the router, not signaling to all the hosting or all the systems in the subnet. So that's why we need 2 different reserve addresses for the functionality. You can see the TTL as equals to 1, which is not going beyond your subnet or the VLAN area. So that's quite important to recall in terms of understanding. All right, now we are at this stage. Okay, now the receiver 2 previously requested to exit or leave the group, not intended to receive anymore, and the router get the message, and the router is following up. Does anyone need your group need multicast from group address this? and then receiver one got the message and responded that I still need this, and then the switch will stop sending multicast message to the receiver 2. There onwards, receiver 1 is only getting the message thereafter. Non-receiver will never get the message because it doesn't signal. So now the leaving, now receiver 1 is the only one receiving the message, the multicast messages. Now receiver 1 wanted to stop receiving the message or multicast stream. It's signaling that I don't require this stream anymore, and that is the only host available in the network, local area network or VLAN. And then it's automatically exited from this, and router is started following up. So router is keep on sending following up because the receiver one signal that I don't need this stream, and sending a leave message or just exiting from the message without sending a leave message. Now router need to follow up if there are any other receivers in this network. Again, it will be sending the follow-up message to all the host here, 2240.01. And then if any host not responded, then after 1 second, it will send another message to follow it up after waiting for some time. Then it'll if there is no response to the second follow-up, then it will send another one after t+3 time, which means t+3 t is the optimal time tune for the follow-up messages, and after each second, and thereafter it will be following up, and no response from group membership query, and no host listening from this. After the t+3, then at after 3 seconds, it will stop sending any more traffic to the switch there onwards. So that's the usual way of processing the working on the IGMP version 2. This is quite important to get understanding how to maintain the state tables on the router and sending the multicast traffic on demand, and how to leave the traffic based on IGMP version 2. Version 1 does not have the leave mechanism, but it automatic follow-up mechanism, which we are not discussing the details here. All right. Any questions until this point before we move to something called IGMP snooping?
No, sir.
All right, that's fine then. Okay. Anyway, I'll be sharing these slides with you today night, and probably you can understand the step-by-step going through each and every slide. And so then let's move to the step of understanding IGMP snooping functionality. So IGMP snooping, okay, IGMP snooping is necessary due to the functionality of a switch. Hope you can remember that switches are layer 2 devices. This is represented, this is not with a multi-layer switch. This is a representation of a layer 2 switch. So usually these routers are layer 3 devices, right? So internet protocol, IP, is usually on the routers. The switches are just forwarding based on MAC addresses by creating a MAC address table, as I shared you on the last week 1004 course appendix, which is a recap. So switches are layer 2 devices. So how does, if you go back to the previous protocol mapping on the TCP/IP stack, you can find out that IGMP is a protocol not on the layer 2, right? IGMP is a layer 3 protocol, similar to ICMP, or the some part of it's on the transport layer as well. The layer 3, then switches does not have understanding of IGMP protocol, because it's only operating on the layer 2 domain, which is the data link layer of OSI model. But how the switches are handling this? Usually, traditionally, none of the switches were supporting, traditionally, the switches were flooding the network. The routers are quite filtered with the implementation here, because IGMP is a layer 3 protocol and routers are layer 3 devices, and it's quite capable of handling IGMP. But this, the filtering by IGMP unable to proceed done on the switch level, because it doesn't have the layer 3 capabilities. It's just the later link layer capabilities are there. So the earlier days router switches or the network segment are flooded with the IGMP, the usual the multicast traffic, because it doesn't have the IGMP awareness, which and flooding, if multicast received from the upstream router based on a request from the first receiver, it's flooding to the non-receivers as well. That's the behavior of all the switches, the first gen switches. Then later people realized, that network designers realized that since IGMP is a layer 3 protocol or layer 3 and above protocol, we are unable to filter the multicast traffic on the switch level, or the layer 2 multicast cannot be filtered in this by using layer 2 switches. So then they if the layer 3 switches are quite expensive, you can't recommend always having layer 2 and 3 multi-layer switches, because those are expensive. Then the network designers started including the IGMP route processor on all the modern day layer 2 switches. So now if you purchase any enterprise grade switch for your network implementations, usually there is a switch processor which is based on ASIC circuits, plus it's automatic included IGMP route processor as well, not generic IP routing process. So all the new modern day switches included to filter layer 2 multicast traffic by including IGMP route processor. So that's how it's controlled. That's how the layer 2 switches getting understanding of the IGMP layer 3 traffic to filter it up. So you can see that in this diagram, once the receiver 2 signaled its exit requirement to leave the group, sending through the switch. Now switch has this IGMP route processor, and it was able to listen this IGMP messages due to this new IGMP route processor introduction to new modern day switches. So it's just listening the messages sent through its own switch with the IGMP protocol. And after it's seen the leave message, it will automatically block this port. That's how it's blocked at the switch level or layer 2 switching level. Otherwise, usually layer 2 switches are not supported this functionality. So all the modern day switches are comprising with the IGMP route processor and capable of listening these IGMP messages. And once it's receiving the leave message, it will automatically block this particular port from that receiver who signals the exit. So that's called IGMP snooping, right? So IGMP snooping, you can disable or enable, because previously everybody flooded with a multicast. If multicast received from the switch, one of the switch ports or upstream router, it will flood all the receivers and the non-receivers. Now you have IGMP snooping enabled, then you are quite capable of not sending traffic to non-receivers or the people who exit from the or machines who exit from the multicast group by sending a leave message. So this is the idea of implementing IGMP snooping. Most of the modern day switches are by default enabled with IGMP snooping to avoid flooding of the network. That is one of important information in terms of you can check whether any of the switch you purchase IGMP snooping disabled, by default disabled or enabled. Most of the switches are nowadays are enabled for the optimization. If you are interested on flooding it or have your application not supporting IGMP functionality, then which is having traditional implementation, then you can still disable IGMP snooping. So that's the importance of IGMP snooping. This is quite important. So by default, switches forward all traffic to multicast frames to all the ports except the originating port, similar to the one the functionality of a switch. Initially, if you don't have a MAC address, you are flooding it to all the traffic, even unicast traffic other than the originating port. Traffic will be flooded. That's called unknown unicast. But multicast, again, by default, switches having the same feature. If any multicast traffic received by a MAC address of all F or the multicast group address, it will forward to all the switch port other than the originating port. But with this IGMP snooping, then you are forwarding only to the relevant router ports or the relevant receiving ports. So now modern day switches with IGMP snooping or IGMP route processor, quite capable of blocking the ports who are not interested or signaled receiving the multicast. And IGMP snooping is on by default on all the modern day switches. Now there was a previous before IGMP there was a protocol named CGNP, which is Cisco Group Management Protocol. Now Internet Group Management Protocol is a standard for all the vendors. So you can it is important in terms of IGMP protocol and IGMP snooping as well to implement layer 2 multicast functionality. Okay. So this is for the explanation in terms of host only receiving multicast traffic that they requested. All right. So I think we can wind up for a break. So I will put a timer on that. After 15 minutes, we can join on 10:45 for the next sections. So we can discuss on the tree building process and the layer 3 multicast on the second session. Right. Let's meet up on 10:45. Thank you.